Bismillahirrahmanirrahim. In this video series, we'll go over General Chemistry for Engineers for preparatory year Faculty of Engineering, Cairo University. In the past few months, I've got several requests to record this series in English so that our foreign students can follow along better. So here we go. An overview of what we'll discuss today. A brief introduction of the teaching assistant and the subject we'll be teaching or explaining in this video series, the grading of this subject, and the first topic of today, which is the building materials. Inside the building materials, here are the headers or the topics that we'll discuss. First topic will be mortar and then cement, and we'll focus on most of today's tutorial will be focused on the ordinary Portland cement, which is the most common type of cement used around us, and then we'll briefly mention other types of cement as well. Okay, so let's start with the introduction. My name is Samer Hani. I'll be recording this entire video series in English this semester, and actually I'm teaching 4 classes this semester as well in Cairo University. I'm typically there all Wednesday every week, and I've actually got a couple of foreign students in my classes, so I hope this helps them inshallah, and all of the foreign students in this year's class. Okay, so let's start with the grading of the subject. We've got a total of 100 marks, 60 marks for the final exam and 40 marks for the year's work. The midterm will be 20 marks, and the section or the classwork together in the classes will be 20, the other 20 marks, 10 for the attendance, and then we'll have 2 quizzes, and we'll take the highest score, but you need to attend both quizzes. And for the lab exams, we'll study a couple of experiments together after the midterm in the lab, and you'll be tested on 2 of those experiments, of course randomly. Everyone will pick 2 random experiments to be tested on at the very end of the semester. Okay, so before starting on our first topic, let's just give a brief introduction of our scope in this subject this semester. So General Chemistry for Engineers is not pure chemistry. We're actually interested in the industrial scope of chemistry. So the first 2 topics we'll discuss will be industrial applications of chemistry. The first one will be how to produce the cement, and the second one will be how to produce lubricants, and we'll discuss all different aspects and factors like you'll see today shortly. And then we'll go into calculating all parameters for ideal gases and real gases, for pressure and volume calculations, temperature, and everything. After that, we'll go into the thermochemistry and combustion reactions, because like most or all of industrial applications will somehow have like a furnace or a heating application or something of that sort, where we burn some fuel to get some energy, and by calculating the amount of energy required, we can then use thermochemistry to deduct and know how many, or calculate how much fuel we need and how much air we need for that fuel to be oxidized or burned or combusted. And then the last topic of this semester in this subject will be discussing the different pollution effects and how to calculate the different parameters of pollution and pollutants, and that's it for our subject. All right, so as you can imagine from these topics, we don't dive into the pure chemistry of organic reactions and inorganic reactions. So if you're worried about this, don't be. It's very minimal that we have to memorize long reactions and stuff like that. Okay. All right, so let's get started on our first topic today, which is the mortar. What is mortar? The mortar is the paste we use in building to help the coherence of its components. So it's actually the paste that we see the workers working with when sticking together two blocks for building a wall or any building unit. So this paste that we use is called mortar, and this is the paste responsible for sticking the components or building blocks together to create a whole unit, a whole consistent unit, and giving it some strength. Okay. We have two types of mortar: the aerated mortar and the hydraulic mortar. The mortar generally consists of sand in both types here, and an active ingredient that reacts with something to harden or become solid. Okay. So in the case of aerated mortar, it's slacked lime. The slacked lime is calcium hydroxide, which reacts with air, or specifically carbon dioxide from air, and hence the naming aerated mortar. And the products of this reaction are calcium carbonate and water molecules. Okay. As for the hydraulic mortar, it's sand plus cement. And this cement is the active ingredient that reacts with water to harden and solidify, and hence the naming also hydraulic, coming from water. Okay, we'll not discuss the exact reactions here because they are multiple reactions, not just a simple reaction like the aerated mortar. And we'll discuss these reactions in a couple of minutes in this tutorial. Okay, so why do we see hydraulic mortar very often and not the aerated mortar? Because from a strength point of view, the aerated mortar is much weaker than the hydraulic mortar. So it's mainly used when there's no water present, or the water is scarce or expensive, is an expensive resource where we want to build something like in the desert, or we're building something that's very small that will not have to withstand high load, like building a fence or a wall for in the desert for military purposes and stuff like that. But for the hydraulic mortar, when we want to build some units or entire buildings that will have to withstand very high load, we need to use the hydraulic mortar or the cement, especially when we're using it in concrete to build ceilings and concrete blocks for withstanding high loads above them. Okay. All right. So first off, we'll focus on the cement, because this material needs to be produced in very, very large amounts, because we use it in all the buildings around us. So it's a very essential compound or product. And the most common type of cement that we use, the gray cement that you see everywhere, is called the ordinary Portland cement. Why Portland? Because actually this cement was found first not a synthesized material or product. It was actually found in nature in Portland. And once we discovered this material and discovered its properties, the strength it gains when it reacts with water, we started experimenting and checking and analyzing the components inside that product to be able to produce it industrially on an industrial scale later. All right. So this is the ordinary Portland cement, which is OPC for short. And to produce that cement, we need some raw materials. The raw materials are limestone, which is calcium carbonate, the clay, which is aluminum oxide and silicon oxide bound together with two molecules of water in their crystal structure, and some, to a low extent, some ferric oxide, and we'll see what this ferric oxide does or how it benefits our reaction. So the cement is actually composed of four main oxides. The main oxides are calcium oxide, aluminum oxide, silicon oxide, and these are the components responsible for most of the functionality of the cement. And as we see here, there is some ferric oxide, which is not always present in all types of cement, but it's an addition that we use in producing ordinary Portland cement. Okay. Okay, so some notes here. The ferric oxide addition or additive helps the formation of clinker. The clinker we'll discuss later in a couple of minutes, which is the intermediate product in the production of cement process. So it helps the production or the formation of clinker, which is formed in the main reactor in the factory at lower temperatures, around 1300 degrees Celsius. Normally without ferric oxide present in the mix, this reaction will be at 1400 degrees Celsius instead of 1300, and this of course saves us some energy and some fuel and some cost when producing the cement. And this ferric oxide is actually the main reason that the ordinary Portland cement we see is gray instead of white. So if we want to produce white cement that we use for decorations, it's basically the same, but we don't add this ferric oxide, and hence the higher price for white cement than or compared to the ordinary Portland cement. A second additive that we add is the calcium sulfate or the gypsum. The gypsum is calcium sulfate dihydrate, 2 molecules of water. This is added to retard or make the setting or solidification of the cement mix, the mortar or the concrete slower. So it's a retarding agent to give the workers some time to be able to form the cement or the mortar and work with it before it starts solidifying. Okay, this is added to around 5% of the total mix, and we'll see in our production process right now in which stage it's added. Okay, the main components of the ordinary Portland cement, which are the components responsible for its functionality, are calcium silicate. It's 2 calcium oxides linked to 1 silicon dioxide, and for short, so that we don't need to type all that name every time we want to refer to dicalcium silicate or the entire chemical formula, we just type it as a shortcut here, dicalcium silicate. So it's C2, 2 of the calcium oxide with 1 silicon dioxide. And as we said, the cement is composed mainly of oxides, 4 oxides. So when we see this C, it stands for calcium oxide. It's not calcium alone, and it's not carbon, because this is not a chemical compound. It's just a shorthand representation for this compound. Okay. Same goes for tricalcium silicate. So 3 calcium oxide moles linked to 1 silicon dioxide mole, and it's called C3S. Tricalcium silicate, 3 calcium oxide moles with 1 aluminum oxide, so it's C3A. And then the 4th compound here, which is formed due to the presence of the ferric oxide, is tetracalcium aluminum ferrite, and its shorthand is C4AF, as we see here. So 4 calcium oxide, 1 aluminum oxide, and 1 ferric oxide. Okay. So for the production process, we take these raw materials. Okay. And the first step is they go into crushing, because we just got these raw materials from the quarries, and they are in big bulks. So we insert them in the first stage into a crusher to crush them into smaller bulks or smaller stone size. Okay, let's actually see this crusher in action. So here's the crusher, and let's just go over. Okay, this is called a jaw crusher. the jaw crusher because it represents it's shaped like a jaw, and this is a stationary. Sorry. Okay, the pen doesn't work. So this is a stationary side, and this is a moving side. And as you see, it's linked to a motor that just simulates a jaw opening and closing, and all of the bulk materials going in from the big opening gets crushed into smaller size stones or solids, and goes out from the smaller opening at the bottom. Okay, let's go back to our process. So after crushing, we take these solids mixed together in the crushing stage into a mixing tank, and this mixing tank we add some water to help create a consistent mix or a consistent paste. And actually the method of or the process of production of the OPC that we're studying right now is called the wet process of producing OPC. Okay, because if you research online and check, you'll find multiple processes that are used to produce cement. The most common are the wet process and the dry process, and we'll just study the wet process this semester. Okay, so in the mixing tank we add water to create a more consistent mix, and after the mixing we go into grinding. Why we want to grind the material to increase the surface area and gain some consistent powder, and mixing powders is easier and will produce a more consistent mix than having some bulky solids. Okay, so in this grinder, this is a ball mill. Okay, this is called a ball mill. It grinds the smaller bulky solids coming out of the crusher into some fine powder in here. Okay, let's also see how this grinder works. So this is called a ball mill. It has some bolts inside of a harder material than the raw materials that we're using. Okay, let's just mute the voice. Okay, and it's a cylinder, a hollow cylinder that rotates around itself with some hard bolts inside of it. Okay, and we insert the material into this grinder or ball mill, and when the balls, like you see here, when the balls drop, they drop on some other balls and the raw material bulky solids. And since the balls are harder than the material, we want to grind and make fine, like fine powder. These raw materials will be crushed further and will, in the end, be produced or outlet as fine powder. Okay. All right, let's go back. These videos are in the PowerPoint presentation. You can watch them and repeat them as many times as you want. So after grinding, we go into a filtration stage, and this filtration stage we just remove some of the water, and actually most of the water that we can remove. Why do we remove the water? Because after this filtration stage, we want to go into the main reactor, and in the main reactor, as we discussed earlier, we want the temperature in there to be around 1,300 degrees Celsius, and we don't want to inlet some extra water so that we need to expend or give some extra fuel and some extra energy in that reactor to vaporize that water. So we insert this filtration stage in here so that we can remove most of the water that we can before going into the main reactor to not increase the thermal load on that reactor. Okay, so this filter just removes two streams, or splits the mix that's going into it into two streams. For this drum in the middle, this drum just suctions the water, and this water is recycled to this mixing tank, and then the solids go into the main reactor. So the solids are retrieved from this knife, and we can actually also see how this filter works. So this is called a rotary filter. This rotary filter consists of a drum that's rotating, and as you can see, there's a sink here in which we insert our materials, the suspension of water and solids, and this drum rotates around itself, and you can see the drum surface is actually a filter fabric, and this pipe is linked to a suction or vacuum pump that suctions the water off the surface, and the solid cake resides on the surface. It can't go into that drum, and once the drum rotates around itself, it goes to this, like you see in this sloped knife, and this knife scraps the solid layer or the cake layer off of the drum, and the drum keeps rotating around itself. All right. So I think, yeah, there's an animation here. So as you can see, the solids cannot go into the filter medium. The suction takes most of the water, actually not all of the water, and then this knife scrapes all of the solid or cake off of the surface of this filter drum. Okay. So this cake here, the cake produced, is mostly solid mixed with some water. So we have removed most of the water that we can remove, and then the remaining water we can just get rid of or vaporize inside the reactor. All right. So let's go into the main reactor. This main reactor is called a rotary kiln. Rotary kiln. It's just a furnace. A furnace with some fuel and of course plus air here. This is the flame. The flame is actually at 1500 degrees Celsius, so that it can bring up the solids or the raw materials that are rolling here and bring them up to 1300 degrees Celsius, so that the reaction can happen inside the reactor. So this drum or rotary kiln rotates around itself and is sloped. As you can see, it's not that sloped in reality. It's just in this diagram so that we can emphasize that it's not totally horizontal. Okay, so there is a certain angle theta here, and we'll discuss the degrees later on. Okay, and the air just goes up like this, while the solid raw materials mixed with some water go down like this, and they interact or directly interact with each other, so that some heat transfer takes place from the very hot air to the solids. The hot air leaves here at around 400 degrees Celsius, while the solids inputted into this reactor at like the room temperature, and then go up to 1300 degrees Celsius, so that they can react with each other in presence of ferric oxide and form the four main components that we just discussed: the C2S, C3S, C3A, and C4AF. And actually we get clinker solid. This is the intermediate product that we discussed in a previous slide. The output of this kiln is clinker. Okay, this is the intermediate product in the process of producing the cement, which is just the main product of the reactor without any additives added onto the cement. Okay. Alright, so this clinker here is at about 1300 degrees Celsius. We need to cool it down, so we have a rotary cooler in here, okay, which is just a cylinder that's just rotating to help the clinker produced in the kiln to slide down the cooler, and then cool it down. How do we cool the clinker here? We insert some ambient temperature air. We just grab air from the surroundings and insert it into the cooler, and then the air goes like this in a counter motion with the solids produced from the kiln or the clinker, and cools it down. And this air, actually, we don't just throw it away after the cooler. We take it, it's got some thermal energy from the clinker, so we don't want to waste this thermal energy inside of that air, so we use it in the burner here with some excess air from the surroundings. Okay, and this depends on the calculations that we'll discuss in the thermochemistry chapter. All right, so the clinker leaves the cooler still a little too hot, so we do a further cooling stage, which is the clinker pile. This is just a pile of clinker to let it cool slowly until it goes down to around this, the surroundings temperature or the ambient temperature around us. Okay, so this is just a pile in an open area. We just pile the clinker and let it cool for some time. Okay, and then we grind this clinker, because the clinker produced from this kiln is porous balls of solid, which are like 1 to 2 inches in size, so they're not actually powder. And we take this clinker after being cooled and insert it into the grinding phase, or the ball mill. This is also a ball mill, or could be any other type of mill. Anyway, we grind this clinker to produce fine powder cement, and we add all of the additives we need for that cement in here, which is mainly gypsum, and if there are any other additives, we can add them in this step, since it will be mixed thoroughly with the cement, the clinker, and produce the cement. And the last stage would be just to pack this cement into 50 kilogram packs, and then we've got the final product cement. Okay, so a couple of notes here, or points to discuss before going further. First off, some information about the reactor. The main reactor is 3 to 4 meters in diameter. The length of this reactor is 60 to 120 meters. And it's sloped like 5 to 6 degrees on the horizontal level, which is too low. You wouldn't even notice it if we drew it here in this slope. But this is, as we discussed, to emphasize that it's actually sloped. The speed of rotation for this reactor is 1 to 2 RPM, or round per minute, or revolution per minute. And the clinker size leaving the reactor is 1 to 2 inches, or 3 to 6 centimeters. Okay, so that's for the reactor. Let's also discuss something very important before moving forward. In this stage, after producing the cement and we have cement, we can't just go and sell it in the market. We need to first make sure that it's according to standards. So there is always a quality assurance or quality control step to make sure that our product, no matter which product we're producing right now, and it doesn't even need to be a chemical product in any industry, we need to pass by a quality control or assurance step, where we do some standard tests to check if this product meets the standards for the product or not. Okay, so that's what we'll discuss later. Before moving forward, we need to know how will we determine if this cement is according to standards or not. Okay, so after producing the cement, we need to know now the reactions this ordinary Portland cement goes into with water. Okay, so we said we have 4 main components, and we can say in here there is C4AF, because this this compound plays a similar role to C3A. so it's not present in here as an individual product, and it's always in a small percentage. Okay, so we won't go into the chemical reactions themselves. We'll just mention which component of the main cement component is responsible for which role or which function in the solidification and hardening of the cement. Okay, and the reaction time, which is the most important factor for us right now. So the reaction time for C3A is 6 minutes to 3 hours. So it's the fastest component to react with water, and as we said, C4AF plays a similar role to C3A. So this is responsible for the initial setting of the cement. So the initial solidification without any strength, just transforming from a paste into solid. No strength yet. Okay. Second is the C3S, the tricalcium silicate. It takes about a week to react with water, and it's responsible for setting as well as the early strength. This compound is responsible for the strength of the concrete in the early stages of time. All right. Lastly, the C2S is the slowest to react with water. It reacts with water in like 4 weeks and continue the reaction for the following several months. And this is responsible for the long-term strength of the concrete. So as time goes by, the concrete gets stronger because this component here is still reacting slowly with water over time. All right. And if we check this comment, this just says C4AF just plays a similar role to C3A, but to a weaker extent. And it's not present in a very high percentage also. So this is just a schematic diagram, not to scale, of course, just to show us the strength of each compound. So the C4AF reacts faster than the other compounds with C3A and C3S. So C4AF is very weak here. The strength level is very weak, and C3A is just above it. Okay. And for the C3S, it starts, this could be actually a little slower in the beginning and then rising fast like this. Okay. So C3S reaches a very high strength level, and this is why it's responsible for the early strength of the concrete. And C2S will start slow at the beginning because it can't compete with C3S reacting with all of the water. And after the C3S is almost done or completely done, the C2S compound starts reacting somewhat rapidly with water or to a faster extent, and goes to nearly the same strength level at the end of the reaction. Okay. All right. So let's dive into the quality assurance tests. The first standard test is the hydraulic factor. The hydraulic factor just measures the relative amount of calcium oxide relative to all of the other oxides in the mixture or in the cement. Okay. And this, let me remove the marks. And this range for this hydraulic factor, let's say this is HF. So HF must lie in the range 1.7 to 2.2. You don't need to memorize this expression. You just need to know what it represents or what it measures, and the range for that particular factor, and what would happen if we lie outside the boundaries, whether it's lower than the minimum or higher than the maximum. Okay, so if the hydraulic factor is lower than the minimum, this means that C3S will be formed to a lower extent than the standard amount. Why is that? Because the calcium oxide is actually the main oxide that reacts with all of the other oxides in all of the compounds. All of the compounds start with C, of course, because it reacts with all of the compounds. And if we see here, the C3S has a very high content of calcium oxide, and we have another compound, the C2S, between calcium and silica, which has a lower extent or a lower concentration of the calcium oxide. So when this amount of calcium oxide gets lower, the reaction will actually go and be directed more to the C2S than the C3S, since there is no enough calcium oxide to react to form the C3S in the proper amount. Okay, and if we know the features and functionality and the roles of each of the components, we can actually know exactly what would happen when one of them is affected by making it higher or lower than the standard amount. So since this C3S was responsible for the setting and the early strength of concrete, then a lower amount of C3S will result in a slower setting and lower early strength. Okay. All right. So what happens if it exceeds the maximum? Then we have free lime in the cement. Free lime, as in the calcium oxide already reacted with all the available other oxides, and there is some more calcium oxide that didn't find any oxides to react with. And why is this a problem for us? This calcium oxide is the quicklime, if you know quicklime from studying chemistry before. This reacts with water and produces high amount of heat. So this is a high exothermic reaction which produces heat. And what would happen if we have some concrete block like this with an exothermic reaction happening inside of it, and there is some water around this reaction? The water will start vaporizing and bubbling inside that concrete block, and this water vapor the pressure will keep increasing as this reaction goes on and the temperature increases, and this eventually will come to enough pressure to create its own path and get out of the concrete block. So it will produce or result in some cracks in the concrete, so that the water vapor can go through them and go out of the concrete block. Okay. This test was actually replaced with a newer standard test, which is the lime saturation factor, LSF. And this just takes into account that when analyzing the cement, not all of the calcium oxide is actually from the clinker or in the main components of the cement. Some calcium oxide actually got into the mix from adding the gypsum, if you can remember, from the additions in the last ball mill. So this is just a correction factor to adjust for the amount of calcium oxide coming from the gypsum, and some coefficients to adjust for the mass balance. Anyway, as we said, we do not need to memorize the expressions. We just need to know what this test is actually measuring or representing. Okay, so of course the LSF will produce different results numerically, and the range will be different. So it's between 0.66 and 1.02. But the same goes if it goes lower than 0.66. The same goes as the hydraulic factor, and if it exceeds 1.02, it's also the same with free lime. Okay. All right. So moving forward to the next test, which is the silica index. The silica index just measures the relative amount of silica or silicon dioxide to the other oxides in the mix. Okay, except for, of course, calcium oxide. All right. This range is from 2 to 2.5, and if the silica index goes below the minimum, which is 2, let's focus first on these two compounds, which has a higher percentage of silica. So let's type them in here: C2S and C3S. For a mole percent, this has 1 silicon dioxide to 2 calcium oxide. So by mole, this is 33% by mole. Okay, we can convert this to by mass, but we'll just represent it by mole for now. As for C3S, this is 25%, because 1 silicon dioxide inside the entire compound, which is composed of 4 different moles or molecules. Okay, so C2S has a higher percent, and C3S has a lower percent of silica. When the silica goes below the standard range, that means the compound with higher silica percent will be formed in a lower extent, and the compound with the lower silica percent will be formed in a higher percent. Okay, so that's what these two actually represent. So C2S, which has higher silica content, will be formed in a lower concentration or a lower amount, and C3S, which has lower silica content, will be formed with a higher amount. And consequently, C3A will increase because we didn't consume as much calcium oxide since the silica is already down. Okay, so setting and solidification will be very fast since C3A and C3S are both up in the amounts. Okay, and the reverse happens if the silica index falls above the maximum or exceeds the maximum limit here. So the C2S, which has higher silica content, will be formed in a higher amount than usual, and C3S and C3A will be formed in a lower amount than usual. So this indicates slower setting and lower early strength of the concrete, since C3S is lower. Okay? Alright. The third test is the magnesium oxide percentage, and this percentage should not exceed 5%. A higher percentage of magnesium oxide means that the quality of the used limestone is poor. This should surprise you, magnesium oxide. We didn't mention magnesium oxide in any of the previous slides as raw materials or as additives or additions to the cement. Where does this magnesium oxide come from? It comes from the limestone or another raw material, which is called dolomite or dolomitic limestone, because in the quarries, limestone is usually linked to, as calcium carbonate is usually linked to magnesium carbonate as well. Okay, unless we have a very pure quarry with very pure limestone, like 99.9% calcium carbonate, it's possible to find some magnesium carbonate linked to it as well. This raw material is called dolomite when the amounts are equivalent, and if we just have small amount of magnesium carbonate, this will be called dolomitic limestone. And this indicates that the limestone is poor for our application or for our industry, because 5% in the mix means that we have more than 5% of our total cement that's not an active material and not responsible for sticking the blocks together and forming some strength. So this is just an inert material, inert solid inside our mix, and it's not helping the function of the cement. So if we calculate our loads and we need like 100 kilograms of cement for a particular application, this means like maybe 5 to 10 kilograms of that cement will not actually contribute to the strength and the coherence of the building unit we're building, and we're underestimating the cement that we're using. Okay, and it will fail at a lower load consequently. Alright, so the particle size, test number 4 is the particle size or the fineness of that cement powder. This standard or the standard for the fineness is that the prepared cement should be very fine, such that at least 98% by mass of it should pass through a screen size of 200 mesh. And the mesh is actually represented by the number of pinches or openings per linear inch. We'll see that in a moment. Here are some standard sieves or screens that we can use to screen the cement sample, and we'll select a sieve or a screen that has a 200 mesh size. How do we determine the size of that screen or the mesh of that screen? As you can see, starting from the bottom left, we have the very big openings at the very bottom left, and as we go to the right, the openings get smaller and smaller, and so on until we go into the 0 opening size, which is the pan. Okay, we want to select one of these sieves or screens that's 200 mesh. How do we measure the mesh? If we take a sample of that screen or sieve, that's 1 inch in any direction, just any linear direction, and we count the number of opening or pinches inside that inch. That's actually the mesh number. So for this particular screen that we sampled, we have 1, 2, 3, 4, 5 openings in 1 linear inch, and this could be also done in the other direction. So it doesn't matter which direction we choose. We just need to choose or sample 1 inch of that screen and count the number of pinches inside. So this would be a 5 mesh screen opening or screen. Okay, and that's how we measure or quantify the fineness of solid powders. Okay, so going back to the screens, let's remove all of the notes. If we select, let's say this is the 200 mesh screen, and we get like 100 grams of cement above that screen and screen them well, we need to get 98 or above % going through that screen, maybe into the pan here. This will be under the screen while we're screening, and only 2% or less should remain above that screen. If it's higher, maybe 5% above and 95% below, this means that our cement is not conformant to the standards, and we need to grind it a little more to make it finer. Okay, and this means, of course, expending more energy, but we need to meet the standards here. All right. The 5th test is the setting time, and the setting time, this test is just done to the setting is, as we discussed, is the initial solidification of the cement to transform into the solid state. Okay, so this test is done to test the speed of cement solidification. Samples of the cement are mixed with standard amounts of water and making like a slab of cement, and that slab of cement will be tested to see how long it takes for it to solidify. So the time at which a standard needle will see the setup used right now with a standard weight cannot penetrate the prepared slab or sample of the cement. Okay, this is called the setting time. Let's see the setup. This is the actual setup on the right, and this is a schematic diagram on the left. So this is a mold that we'll use to prepare the sample, the cement slab sample, and mix it with water inside of it and create like a slab. All right, we'll put that slab in here, like you see, and we have a needle, this needle in here with a cap, and this has a standard weight, which is 300 grams. Okay, and this is just a slider guiding the needle to go vertically and not free fall into any random angles. Okay, so if we look at it from the front view, we can see here the scales. Okay, and we just every minute or every couple of minutes we just take that needle, drag it up, and leave it to fall under the standard weight, and see if it can penetrate this slab in this ring or mold or not. And once it cannot penetrate the surface of that slab, then this is called the setting time. On a stopwatch, from once we prepare the cement sample or slab, we start a stopwatch and then repeat this process over and over again until once we leave the needle, it doesn't or cannot penetrate anymore. Then this is called the setting time of cement. And this is the 5th test that we need to check. And then after measuring that time, we go into the standards and see, okay, is it within the standard time or not? Okay. So the 6th test is the volatile materials percentage. This percentage should not exceed 5% as well, just like the magnesium oxide. And this indicates that the cement has some humidity content in it. And this humidity will actually start reacting with some of the cement inside the packs, and will render it useless, or it will not be used perfectly when we need to apply the cement in the real life. So in storage, these 5% of humidity or more will be reacting with some of the cement and converting it to, or solidifying those particles, instead of having this all of the amount of cement as active materials that will react with water when applied to solidify and stick together. So this means not only did we lose 5% or more of the cement content as humidity, so we're only actually working with 95% of actual mass of the cement. It's actually that this 5% just spoiled or reacted with some of the 95% of the cement and made some of them useless. So we may end up with like 10% of useless mass underestimated in our calculations when we apply. Okay? All right. The 7th and last standard test for the quality control or assurance is the percent of sulfur trioxide. So sulfur trioxide. This should not exceed 3.5% of the total percent or the total mix. And this sulfur trioxide, where does it come from? It comes from the calcium sulfate, right? Calcium sulfate, or the gypsum we added. When analyzing this, this will be broken down into calcium oxide plus sulfur trioxide. Okay? And of course, the water vapor will evaporate. So, the percent of sulfur trioxide given by the analysis should not exceed 3.5%, which is equivalent to 6.5% gypsum. Any more than that means that we've added too much gypsum, and the solidification process or reaction will be too slow for the application. Okay? All right. That's it for the ordinary Portland cement. Now we'll just briefly mention a couple of other types of cement, because it's not only the ordinary Portland cement that's out there, but it's the most commonly used and maybe the only one you've seen in real life applications around you, or maybe you also saw the white cement for decorations. But these other types do exist, and if you look them up or look up other types on the internet, you'll find actually more than these types that we'll mention right now. So the first type is the rapid hardening Portland cement, and this is, as the name implies, this is just Portland cement, but it's not ordinary Portland cement, it's rapid hardening Portland cement. What do we do extra to this Portland cement to make it rapid hardening? We just physically treat them to grind them more, so that it's very fine, such that 99%, 0.5% or lower or higher so must be higher than 99.5% of the mass, pass through 320 mesh screen. So this is much finer than the ordinary standard for the ordinary Portland cement. So it's 99.5 instead of 98, passing through mesh 320 instead of mesh 200. Okay, this will increase the surface area exposed to water during the mixing and the solidification process, and will make the reaction go faster. Okay. The second type is the seawater or the sulfate resistant cement. So this cement will be resistant to seawater or the sulfate salts inside of seawater. In this cement, the silica is added to reduce the amount of C3S formed inside the reactor. Why is this C3S a problem for us in this particular type of cement? This is because in the reaction of C3S with water, it produces a high amount of calcium hydroxide. And this calcium hydroxide, when present, it will react with the sulfate salts or the sulfates in water. So we need to decrease it to decrease the formation of calcium hydroxide in the concrete pores, and hence making it more resistant to the sulfates in the seawater. Okay. The third type is the iron slag cement, and the iron slag cement is, just as the name implies, it's a mix of iron slag plus cement. So it's prepared by grinding the furnace slag from the iron furnaces with the addition of some Portland cement. So we're mixing iron slag, which is, let's say it's a waste of the iron industry or production, and we mix it with some Portland cement. Okay, the iron slag contains the same oxides as in the cement or the ordinary Portland cement, but it's of less quality. So why would we be interested in a cement of lower quality? For two reasons in here. First reason is the price. This will be more economic if we're using the cement for just some simple application that doesn't need to withstand some loads. So we can't actually use it in reinforced concrete. We can just use it to build a wall or something like that. That doesn't have to take in high loads over it. The second reason is from an environmental point of view, we're getting rid or we're actually utilizing a waste of some industry in our product, and this helps the environment because we don't need to find how to get rid safely of this iron slag from the iron furnaces, and spend some money to actually treat that and get rid of it safely in accordance to the environmental regulations. We can just use it as a byproduct into a different product. Okay. So it's not, as we said, it's not preferred since it's of lower quality. It's not preferred to be used in the reinforced concrete. The last type we'll discuss today or we'll mention is the chemicals resistant cement. The chemical resistant cement is used when the buildings or the surfaces are subjected to chemicals. Okay, so a special type of cement is used to cohere its components, or even coat them entirely with a complete coat over the surface of the wall or the unit that we don't want to interact or react with the chemicals and deteriorate as time goes by. Okay, so this is actually the first type of cement that we're not using or treating the usual ordinary Portland cement with some special treatment or addition. This is a completely different type of cement. Just the cement is just the term for cementing or solidifying. Okay, so this cement is composed of some solid material in the form of pellets or fine powder, which are mixed with liquid mixtures to produce a resin product or a polymer that solidifies after a while. So in essence, this cement is just a mixture of two things. The first thing is a solid material to give it some strength. This could be some fine sand or graphite, and some liquid mixture. This liquid mixture is actually a polymerizing mixture that once reacted together, like the epoxies, when these liquids are mixed together and react together, they start cross-linking or polymerizing and create a polymer plastic layer that first off has a sticky feature to it, so that we can stick different blocks together or cohere them together, and it should have some strength to it as well, so that the building unit at the end is strong enough to withstand at least some load. Okay, so the most famous cement in this field is the carbolic cement. The solid is fine sand or graphite or asbestos, and the liquid is a mixture of phenol and formaldehyde. So the phenol and formaldehyde, when they let's say this is liquid A in tube A or in the bucket A, and this is liquid B, when they are mixed together, they start polymerizing and forming a phenol formaldehyde polymer that's mixed with, of course, the solid, and this is used as the paste or the mortar to actually stick the building blocks together or coat them to prevent any chemical reactions, since it's inert to chemicals, to prevent any chemical reactions with the blocks and prevent deterioration of these blocks or corrosion happening to these blocks. Okay, and that's it for the mortar and the cement topic. I hope that was helpful enough and clear enough for you, and see you next time.